Hi, this is Jose Luis, and welcome to another video in this series, Introduction to Parametric Modeling. In this video, we're going to do a hands-on exercise where we're going to take a surface, all right? And then we're going to imagine that it's some kind of roof for the building, and we're going to make these apertures that are going to go, I'm going to go for a square sort of subdivisions of the surface, and they're going to end up into these circular openings. So we're going to imagine that these are some kind of like oculus kind of lanterns or roof-like elements. And of course, we would like to control how many of these elements are in each direction. And of course, we will also want to control how big the aperture of these windows are, how big, how far away they are from the surface, or how close they are to the surface, and all those things that we like doing with parametric modeling, right? So that at the end of the day, we can explore different variations, different versions, and decide which one do we like better, which one goes to production, which one we send to the competition, whatever that is, okay? So this exercise is going to be super interesting. We're going to learn a little bit of more advanced domain subdivisions of surfaces. We're going to learn some properties of how to loft surfaces, and we're going to do a little bit of data manipulation, not too much, okay? So join me on this hands-on exercise, and as we go through the simple version of this exercise first, and then the more advanced, the one that you're actually looking at on these renderings right now. Let's get hands-on. Let's do this. All right, let's get started. So just for a little bit of context, this exercise is inspired by the Kunsthaus in Graz, the House of the Arts, which is basically this like blobby, tentacly kind of building that has these orifices or these openings that are coming out of the roof, and that end in these kind of circles. Obviously, we're going to make like a way more oversimplified version of this. No crazy, we're still beginning, all right? But it's kind of where the inspiration, if I may, where the inspiration came from. So what we're going to do in this exercise is we're going to start off from a surface, and where we want to get to at the end of the day is having a situation where we would like to subdivide that surface into a set of regions, and then we would like to use those regions to extrude those regions, if you will, into circles that could be openings or windows or who knows what. Okay, now this exercise, as I just explained it, is going to require a little bit of additional components and logics that I haven't really explained. So before we do that, I would like to do a simplified version that is going to suck. It's going to be really not great, but this is going to give us like a warm up to how we're going to implement this in the real sense. So instead of doing that, the way I'm going to start is by a simplification, which is going to be, I'm going to subdivide this surface into a grid of UV planes, and we already know how to do this. I'm going to use those planes to create rectangles, just simple planar rectangles that are not going to fit each other, and that's why this solution is not great. And once we have those, I'm going to use those planes also to create perpendicular circles that are offset from that plane, a technique that we haven't seen yet, and then try to figure out if I can fit a surface going from those circles to those rectangles. This will be a okay situation. It's not going to be watertight, but it will be a good foundation for then creating the actual final one, which is going to be the version that I just explained before. So let's take a look at how to create this simpler version first, and then we will revisit how to generate the more advanced version. Let's start. I'm going to start with a surface that I have in Rhino because maybe you generated this surface parametrically, but maybe you were just modeling until you found, like, with your hands touching up and down these points, you found the perfect shape, right? And now what you just want to do is, on top of that shape, apply this logic of creating these windows that pop out of the surface, if you will. So I'm going to assume we have a surface in Rhino that I'm going to bring into Grasshopper, and then we're going to do the typical process of subdividing this into frames. So I'm going to subdivide this surface into a controlled amount of frames in the X direction and the Y direction. So more, less, etc., etc. And now, once we have this, what I can do is I can create, for example, a family of rectangles on top of these planes. So I'm just going to draw some rectangles here, all right? And we already know that the rectangles take domains, so we are going to create here the size of the rectangle in one direction and the size of the rectangle in another direction. And because we did that in the previous example, in the previous video, I'm just going to copy paste that here. So give me a second. So yes, so I just copy pasted this idea of taking a number and create a domain that starts at half the number and ends at half the number. That starts at minus half the number and ends at positive half the number. So I'm going to use that to feed in the dimensions of these rectangles. So now I know that I can create rectangles that are whatever distance. And I'm going to hide this surface so that I can see a bit more clearly. Okay? Now, the next thing that I would like to do is I would like to create those circles that are going to be protruding out of the surface at a controlled distance. So how is that going to work? Well, I could use these frames here. So let me just, for the sake of prototyping, I'm just going to place some circles, and these circles I'm going to be using these frames, okay? And I will have another variable which is going to be the aperture of these circles, and that I can open and close, for example. So I'm going to make them this small. But obviously, I don't want them to be on the same plane. I need them to be on the outside. I need to be them on a plane that is perpendicular to the surface. So how do I do that? Well, it will be just as easy as taking each one of these planes and copying it or moving it in a direction that is perpendicular to the surface. And which direction is that? Perpendicular to the surface is also the direction that is perpendicular to the plane itself. So that is why planes are great. So I'm going to take the plane, I'm going to find what the normal vector to that plane is. I'm going to multiply that vector by the distance, and then I'm going to take that plane, the original plane, and move it by that vector. Let me do that here. So I'm going to take the vectors, each one of the planes. I'm going to deconstruct those. I'm going to deconstruct those planes. Okay, so I have the origin, x, y, and the normal. So now what I'm going to do is I'm going to multiply. I'm going to create another input that is going to be the distance, for example. And then what I'm going to do is I'm going to multiply the normal by that distance. And remember that by definition, planes have unit vectors for x, y, and z. So if I multiply c by 5.23, then the length of that vector is going to be 5.23 because the vector was a unit vector. And now what I can do is I can move all these planes by this vector that I just created. And therefore, I will create a copy that is offset in the perpendicular direction. So I can go here to transforms, Euclidean, move, and then I'm going to move all the frames from the surface. I'm going to move them a direction that is perpendicular to them, but and is controlled by this distance. And it turns out that the original surface was flipped. So I'm just going to show the surface. I'm going to select that surface, and I'm going to type flip so that the internal orientation gets backward so that I can have a positive distance. And if I am correct with what I'm doing, let me hide this again. If I am correct now, you can see that these planes indeed, they look like they're moving perpendicular out of the surface. This, and this, and this. So I think these planes are now the planes that I want to use to create these circles here. And now you can see how the circles are offset from the surface a controlled distance. Okay. Now I'm going to remove all of this and all of these planes to leave things a little clearer. All right. And then the only thing that I need to do left is to create a surface that goes from each one of the rectangles to each one of the circles. So let me show you how to do that. Because it's two curves that I already have in 3D space, probably the simplest way of doing this is by creating a loft between the rectangle and the circle. Okay, so let's try that. I'm going to create a loft that is going to go from the rectangle to the circle. And is this going to work? Let me plug the rectangle first, and then let me plug the circle second. And you can see that quang, 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 it's not working. And it's not working. And it's actually doing this weird thing where it's creating this kind of surface that is going through all the rectangles and then all the circles. Which is actually kind of cool. So let me bake this and take a look at this in a geometry kind of a. So let me take this and wow, this is kind of cool. Let me see this in a render way. Nice. I kind of like this. Well, I don't know what this is, but it's kind of cool. So yes, so now let's go back to fixing this problem. So obviously this is not behaving the way we want it. And why? What do we think might be the culprit? Yes, what has Jose told us? That very likely it's a problem with data. So let's take a look. Let's use a panel to take a look at the data. Okay, so I'm going to press a panel here. I'm going to plug in here these rectangles, and I'm going to take a look at what the structure of the data looks like. It's a data tree. It has a bunch of branches from 0, 0, 0 to 0, 0, 6 with a list of rectangles inside of each. And then I'm going to compare that to what's coming into the circle. All right. So this what's coming out of the circle. The circle has a identical structure. It has the same data tree, same branches, but instead it has circles. And another thing that I recommended in previous videos is that in order to understand how this component is working, because we are plugging both inputs into the same, both wires into the same input, it's a good thing to mimic that process with a panel. So I'm going to plug in the rectangles first, that's what I did, and then I'm going to shift add the circles to the same. And what is happening is that when they both get combined, because they have the same structure with the same branch names, all the elements get combined into the same branch. And as I said in my previous videos, because Grasshopper components work at the list level, then what the loft component is trying to do is to try to create a loft between all these rectangles and all these circles, one loft. And another loft between all these rectangles and all these circles, which kind of makes sense given what I'm seeing here. I see like a surface that is kind of sweeping and lofting over all these rectangles and then wraps up and tries to do all these circles. So I think we have identified the problem, but now we have to figure out the solution. So what we want is surfaces that only join one rectangle with one circle, another rectangle with another circle, another rectangle with another circle. So if the loft component works at the list level, I need to figure out a way to create lists that only contain one rectangle and one circle. One rectangle and one circle, one rectangle and one circle. So the way to do that is, what do you think is going to be? As we said, we can do grafting or flattening. Which one of those two are we going to try? If I flatten, it's going to be worse because all the rectangles and all the circles are going to be on the same list. And when combined, I'm going to have one single loft that is going to go through all the geometry. So I need to do the opposite. In this case, what I need to do is I need to graft a tree for this one, and that will give me a circle per branch. I need to graft the tree for the rectangles, and that will give me a rectangle per branch. Oh, correct? And then when I mix them together, so when I plug in here the rectangle, and then when I plug the grafted circles, you can see that because they have the same structure, when they get combined inside of branches, now I get a branch with one rectangle and one circle, another branch with one rectangle and one circle. And therefore, if I do that here, I'm going to get the rectangle, and then I'm going to shift add, and I'm going to get the circle. All right, is that true? Yoo-hoo! It's kind of working, but not quite. What is this weird torsion that is happening in the, this is not great. I mean, could be great if that's what you're shooting for, but I kind of wanted something that it was more of a straight kind of loft, sort of between them. So this is clearly not working. And it's not working just because lofting has a bunch of options that allow me to control how the loft is working. And in this particular case, the error that is happening is that the internal domain of the rectangle, so where the rectangle is at 0 and where the rectangle is at 1, might not be aligned with where the circle has its internal domain starting at 0 and starting at 1. Even though they're both close periodic curves, I don't know, here, their start points and the end points might not be aligned. They might be twisted like this. And therefore, if I don't tell loft otherwise, loft is going to try to create a loft that aligns the internal beginnings and the internal ends of these two curves. So how can I solve this? Well, turns out the loft component has an input called Loft Options, and I can generate here with Loft Options, I can generate an object called Loft Options that I can plug in here, and then I can control some of the parameters of how the loft is generated. So we can have a different kind of loft type, loose, tight, strays. We can refit the loft, we can rebuild it, and we can do something that is called adjusting the seams. I'm not going to get into all these options, but adjusting seams, what we'll do is that it will align those two, it will align the beginning and the end. So if I add a Boolean toggle here and I turn this into true, you can see that the lofts are now nicely aligned. The two curves are nicely aligned with each other. The seams are aligned. So I have been able now to generate this approximation to taking a surface and populating it with this kind of apertures that go from a rectangle to a circle. However, this is not where we want it to go, because what we want is actually watertight, nice, solid. We could not make a roof out of this. Like, our client would kill us, you know? So let's take a look at how we could change this to make it now actually watertight. Okay, let's take a look. As we said before, we can start with the surface, but instead of subdividing it in frames, whatever, we actually want to be really, really faithful to the original shape of the surface. And we want to make sure that the extrusions land exactly on the surface. So in this case, we're not going to be able to just generate any square. We're going to have to work with contours that are actually exactly contained on the surface. So what we're going to do is we're going to divide the original surface into patches, so smaller chunks of surfaces that are going to be smaller parts of the larger surface. We're going to divide the surface, instead of UV frames, we're going to divide them in UV patches of surface, or I think in Grasshopper terms it's called Isotrims. So we're going to do that. And then after that, for each one of those new surfaces that I'm going to obtain from the original one, I'm going to find the plane that is going to be more or less on the center of that surface. And I'm going to move that plane perpendicular so that I can draw a circle that is offset from the surface. And once I have that, then what I'm going to do is I'm going to take the surface and I'm going to extract the contour lines. This time it's not going to be a perfect planar rectangle. It's going to be the lines that are the contour of the surfaces. And I will use that curve in 3D space, the curve that is the edges of the surface, to loft these openings that are going to go not from a planar rectangle, but from the 3D contour of the patches into the circles that I have created up, that I have offset from the surface. How is that going to work technically? Let's take a look. So I'm going to start off from the definition that I had, but I'm going to turn off everything, and I'm just going to create I'm going to create a new version here underneath. And then this is going to start with the surface. And then, as I said, the first thing that I would like to do is I would like to subdivide the surface into patches, or I'm going to basically cut the surface into smaller surfaces, if you will. So the way I'm going to do that is with surfaces, utilities, there is a component that is called Isotrim, which means that you need to extract an isoparametric surface of which says that you can extract an isoparametric subset of a surface. What does that mean? Well, that's kind of a mouthful to say that the input is going to be the surface and D is going to be the domain of the subset. What that means is that for example, if this surface was to have a domain that went from 0 to 1 in U and from 0 to 1 in V, I could say, give me the subsurface that goes from domain 0.2 to 0.3 in X and 0.5 and 0.6 in Y. And it will give me a tiny chunk of the surface that is somewhere in that domain space. So, and if you can see the hexagon icon, it's giving me the indication that it's a domain, but it's not a one-dimensional domain like the ones that we have seen before. It's not this kind of domain. It's a domain in 2 dimensions, which means that it has one domain in V and U and another domain in V. So how are we going to handle this? Well, first of all, let's plug in the surface, okay? And then the domain of the subset is going to be, for example, let's do an example where we just take a tiny chunk of that surface. In order to extract a tiny chunk of the surface, I think one of the most useful things that we can do is start understanding what is the domain space of this surface. So for example, one way that we can do this is by taking the surface and say, can you deconstruct the domain of the surface? And if I do that, I can see how, if I plug in this surface here, I can see that U starts at the value of 0 and U1 goes till 32, and V, the domain in V, is from -1 to 0. Another way of looking at this is if I use a domain to empty parameter and I plug in the surface, you can see that the output is the U domain from 0 to 32 and the V domain from -1 to 0. So those are the range of values through which the parameter, this number that we could use to find the location on the surface, through which the parameter can navigate in the U and the V directions. So what that means is that if I want to take a chunk, if I want to cut out a patch of the surface, I have to define an interval in U and another interval in V that I can use to extract that surface. So what I can do is, instead of deconstructing, I can construct a domain in 2 directions from U and V parameters, okay? And then if I plug in here a few sliders, I can say, give me a domain that goes from 4 to 10, for example, in the U direction, and give me a domain that goes from -0.9 to -0.5 in the V space. And if I plug in a panel here, I can see that I have created an interval a domain in 2 dimensions that goes from between these 2 values. Are these 2 values, is 4 and 10, are they inside of U? Yes. And is -0.9 and -0.5 contained inside of -1 and -0? Yes. So therefore, if I plug this in, you can see that I have been able to extract a chunk of that surface that goes from this value to this value in the u direction, and from this value to this other value in the v direction. Okay, so that is a way of just retrieving one single chunk of like one patch of a surface from the overall surface. Now what I need to do is to do this iteratively, so that I make sure that I take the whole surface and I cut it in, like, for example, 3 surfaces in the y direction, in the u direction, and 5 surfaces on the v direction, whatever that is. So what I need to do is I need to perform some arithmetic to take this domain and cut it into u's that go from 0 to 10, 10 to 20, 10 to 30, and then for v, for example, -1 to -0.7, -0.7 to -0.3, something like that. So that would be quite tedious to do manually, but thankfully Grasshopper has some options to do that. So there is one component here on the domain divide domain that is called divide domain in two dimensions. And what this component does is it takes a domain in 2 dimensions and it divides it in a set of segments in the u and the v direction. How convenient is that? So I'm going to take this, which is a domain in 2 dimensions, I'm going to plug it in here, and I'm going to divide this into 2 segments in the u and 2 segments in v. And if I copy paste this, you can see now that this component has given me 4 domains. Or if I do this, it's going to give me 9 domains, which go from u000 and then 3 versions here, 3 divisions for u and another 3 divisions for v, and 3 divisions for u and 3 divisions for v. So if I now take all these 2-dimensional domains and I plug them into Isotrim, what I get is this nice subdivision of the surface in 3 patches in one direction and 3 on the other, or more or less. But we're doing this numerically by subdividing the domain space of the surface. Okay? Yoo-hoo! Well, that took some time, but I mean, arguably, I think it was very interesting because we learned a little bit of 2-dimensional domains, and we also learned about like, we also refreshed like the internal properties of surfaces, domains, u directions, v directions, and parameters. Okay. Woohoo! All right. So we now have the surface patches. Now we need to find the planes that are going to be at the center of those patches. How can we do that? Let's go check Grasshopper. So the way we're going to do that is that typically, perhaps in the past, we would have taken the surfaces and we would have divided them into a grid of UV frames, whatever. But for this one, we're going to go a bit more elegant because we only want the plane that is roughly at the center of the patch. So what we can do is we can analyze the surface, and there is here a component that says evaluate the surface for certain properties of a UV coordinate. What does that mean? I'm going to place this in here, and you're going to see that this component is actually giving me a lot of stuff. So it asks for a base surface. So that is a surface that I want to evaluate or get properties from, and the UV coordinate to evaluate as a point. So it's asking me for a point, but it's not a point in world coordinates. It's a point that is going to be understood as UV coordinates. So, and instead of XYZ, it's going to be UV and W, if you will. And then what it's going to give me is going to give me the point at that UV coordinate, the normal at that UV coordinate, the U direction, the V direction, and the frame. So the plane that will be perpendicular to that surface. So, okay, so how can I do this? Well, I'm going to plug in here the surfaces, that's one thing, and then I'm going to give it UV coordinates roughly from the center. The only problem is that if you remember, these surfaces have domains that are all over the place. So if you remember, the domains of these surfaces are now from 0 to 5 and -1 to whatever, and from -1, so it would kind of take me quite some tedious operations to figure out what the middle of U for this one is and what the center for V this one is, and do that programmatically for each one of the domains. Whereas if the domains of each one of my surfaces were normalized, if each one of the domains in the U and the V directions went from 0 to 1 for each patch, then it would be super easy for me to know that the center is going to be roughly at 0.5, 0.5, and 0. So what I can do is, let me first create a point. I'm going to construct a point that is going to be at coordinates 0.5 for X, 0.5 for Y, and 0. You see that a point shows up here in world coordinates, but don't be mistaken, because we're not going to use this point as a point in world coordinates. The only thing that we need is a point that has 0.5 as the first coordinate and 0.5 as the second coordinate, because if I plug this here, it will not be understood as XYZ, it will be understood as U and V values. And as you can see, no points show up here. I mean, they show up here, but they are all the way out there, because this is where 0.05 of the surface is. What I need to do is I need to make sure that each one of these surfaces, now each one of the patches, has a domain that is normalized. So U and V both go from 0 to 1. And it turns out that in Grasshopper there is a shortcut to doing that. We could do that manually, but there is a shortcut here that if whatever input takes a surface, if I right click and I say that I want to reparameterize this input, what that is going to do is that immediately any curve or any surface that is reparameterized, what reparameterization does is it normalizes the domains of any direction and it sets them to be from 0 to 1. And therefore, a point more or less at the center, remember this is not the right center because of domains can be non-homogeneous, a point more or less on the center will be at 0.5 and 0.5. So now we have all our frames that are at the center of each one of the patches. And then now what we can do is we can follow a very similar process to what we did before. We now take this. I'm going to take and copy all of this. We're going to take the frames and I'm going to move the frames and I'm going to multiply those frames by this height here, and I'm going to multiply the circle. So I'm moving the planes and I'm moving them in -y. Maybe I have to turn this into a negative slider because the surface is flipped apparently. And then I'm just going to do that like that. And then the circles are being drawn here on top of these planes. Okay. All right. So I've basically copied what I had before. So I have now the surfaces. I have now the surfaces, and I have now the circles that are offset from the center. And I also have the frames that are at the center of these patches. So the last thing that I need to do is I need to join the contour of each one of these patches with the circles that I have offset, and I need to join them with a loft. Problem is, though, I do have the surfaces. The surfaces are here, but I don't really have the contour, the edges of these surfaces. Like I said, so the blue lines that I have there. So I need to find that somehow. The way I can do that is by also going to analysis and going to deconstruct brep. If I do that, and if I plug this in here, you can see how this takes any brep, and a surface is a simpler version of a brep if a brep is a brep that only has one surface inside of it. And then it will give me the faces which are it will give me the edges and it will give me the vertices of the B-rep. So if I now plug in here each one of the isotrims, you can see that if I plug in a panel here, you can see that for each one of the 30 surfaces, now what I'm getting is, for example, in the edges, I'm getting a data tree that is 30 branches, and each one of the branches has 4 curves. Each one of these 4 curves is each one of the edges for the isotrim. Now, this is not going to work because I cannot have 4 different curves and then the circle. Because if I do that, and if I love this, it's going to give me something bad. It's going to give me the circle, and it's going to give me this. So it's not going to, not work. Oh, sorry. I plugged into the wrong place. It's not going to give me, you see, it's trying to create a loft around the 4 edges here. So it's not going to work. And also maybe it's, so if I plug this in here, not going to work. So what I need to do is I need to take these 4 curves for each one of the branches, and I need to join them into one continuous curve. That's actually very easy to do because I can go to curves, utilities, and where is join curves. If I do this and I say I want to join all the edges, I don't even need to do any data manipulation because what's nice is that if you remember components work at the list level, which means that this component is going to try to join all the curves that are on the same branch and all the curves that are on the same branch. So how convenient was that this component was giving me edges already in a data tree structure in a way that it made it very easy to join into a closed curve in 3 dimensions. And with this, and with this other tree, I think we are ready to loft, aren't we? So let me loft this, and let me loft this, and then see what the result is here. So, am I not getting any result? Oh, yes. So, I am getting bad results. So, and what is the problem? Data. Problem is data, because you can see that what's happening is that because these branch names are different than these branch names, they are not combined into the same graph when I plug them together. So for example, if I plug them here and if I plug them here, you can see how they're not combined into the same branch, and therefore there's no loft going from the joint curves to the circles. So what do I need to do now? What I need to do is I need to figure out a way to modify the branches so that they have the same exact structure. So how can I do that? Well, there's 2 ways to go about this. One would be I could flatten. So for example, what I could do is I could flatten this so that it becomes like one single list, and then I can graft that, and then it becomes a list with 2 levels. And then I can do the exact same operation here. I'm going to flatten the tree. Here, this becomes a dumb single tree, and then I'm going to graft the tree again, and now it becomes a tree with the same structure. And now I could plug the 2 things in here. So I could plug this graft and this graft. And then here we have it working. Now, that could be one way to go. It's not very elegant. It takes a lot of manipulation. So what I can do is perhaps do a bit more elegant, which is going to be, I'm going to take this, and I'm going to take this, I'm going to take this tree here, and I can see that they have different structures. So it turns out that there is an operation that I can do on trees that is also called simplify. And simplify is an operation that just removes redundant branches that are not really giving information. So the fact that I have a lot of leading zeros here and a lot of ending zeros here is not really helping at all. So if I simplify this, you can see that the tree just gets into a very clean 0 to 30 kind of branch naming. And if I simplify this one, I will get the same result. So now they both have, again, the same data structure, and I can join them together. And now I get the intended result. Woohoo! And last but not least, I'm going to copy this lofting, the one that had the options. Okay, so I'm going to copy the loft options here. I'm going to remove this, and I'm going to make sure that the seams are adjusted, and now I don't have that problem anymore. All right, and let's bake this and make it a little cool, right? So I'm going to bake this. I'm going to do some rendering here. Yoo-hoo! This looks kind of nice. So, ta-da! Now we have the surface that has this like ocular kind of openings, and or like this egg box kind of thing to them, and it could be the roof of a building, or it could be many things. I don't know. Ooh, that was a lot. All right, so I think with this, I'm a little done. I'm also pretty done for today. I've recorded a lot of tutorials today. So thank you very much. I hope this exercise was useful for learning data manipulation, for learning more properties of surfaces in 2 dimensions, 2-dimensional domains, reparameterization, domains, parameters, etc., etc. And with this, I'm going to call it a day. I'm going to go take some rest. And but I will see you on the next video on this series, which at this point I'm not sure what it's going to be. We're going back to lectures, or we're going to do an exercise. I don't know. Just look on the playlist and see what we decided to do next. If this was helpful, if you want to show some gratitude, maybe you want to consider liking the video, subscribing to the channel, and even turning on notifications to see when we go live or when we publish new videos and new content. In the meantime, thank you very much, and hopefully see you on the next videos on this series.